This is the third video or lecture pertaining to difference equations. We're going to look at second order equations and we're going to look at a non-homogeneous case. So the non-homogeneous case can be written as a0 yt plus 2 plus a1 yt plus 1 plus a2 yt equals k. And that's what distinguishes the homogeneous and the non-homogeneous cases. If k equals 0, we have a homogeneous case. Otherwise, it's non-homogeneous. In operator form, we write a0e squared plus a1e plus a2 all times yt equals k. Now, to find a solution, we require two steps. The first is to find the solution to the homogeneous form where k equals 0, and we denote this yt to the h for homogeneous. And we showed how you do that earlier. The second step is to find any particular solution that satisfies the non-homogeneous equation, and we denote this by yt to the n, where the n refers to non-homogeneous. Then the total solution would be yt equals the homogeneous solution plus the non-homogeneous solution. So it's only this second step that is new, and the question then is, would yt equal some constant c satisfy the above equation? If yt equals c, then yt plus 2 equals yt plus 1 equals yt equals c. And we get then that a0c plus a1c plus a2c equals k, and if we solve that, we find that c equals k over a0 plus a1 plus a2, and that is our non-homogeneous solution. But it only works if a0 plus a1 plus a2 is not equal to 0, because you cannot divide by 0. If, on the other hand, that a0 plus a1 plus a2 equals 0, then we try yt equal c times t. If that also leads to 0 in the denominator, then we try yt equals ct squared. If that fails to lead to a denominator that is different from 0, we then try yt equals ct cubed. And we keep doing that as long as we go. So for example, in the above equation, we would have yt equals ct, which results in a0c times t plus 2 plus a1c t plus 1 plus a2ct equals k. And if we solve that, we find that c equals k over 2a0 plus a1, but again, 2a0 plus a1 cannot equal 0. If yt equals ct squared, then we find that c equals k divided by 4a0 a1. So you see, we've looked at three of them. One where we had a0 a1 plus a2 in the denominator, the other one where we have 2a0 plus a1, and the third 4a0 plus a1. And we keep going until we get a solution where the denominator is not equal to 0. So for all three solutions in this particular case, yt equals c, yt equals ct, and yt equals ct squared, for those to fail implies the following equations must have a non-trivial solution. That is, where the solution is not simply a0, a1, a2 all equal to 0. So we get these three equations, and one can demonstrate that there will always be a solution to the nth order equation, even if it occurs when yt equals ct to the n. So let's look at an example in the case of yt plus 2 minus 3yt plus 1 minus 10yt equals minus 12. We assume that the first order conditions are that y0 is equal to 9 and y1 equals minus 1. In operator form, take this equation and it becomes e squared minus 3e minus 10 yt equals 0. So now we're looking at the homogeneous component. Characteristic equation is x squared minus 3x minus 10 equals 0, which gives you x minus 5 times x plus 2 equals 0. So x is either equal to 5 or x is minus 2. So the homogeneous solution then is k1, 5, which is our x1 value, to the power t, plus k2, minus 2 to the power t, where that minus 2 comes from here. Information from the initial conditions is not used, however, at this point. All right, so these numbers come from the characteristic equation solution. But now we can't use information from the initial conditions until we complete the general solution by including in it the non-homogeneous component here. So for the non-homogeneous part, we first try yt equals c, which gives us 1 minus 3 minus 10 times c equals minus 12, and c equals 1. Then the general solution is simply yt k1 5 to the power t, k2 minus 2 to the power t, plus this 1, which is the solution to the non-homogeneous case. So now we employ the initial conditions. We find that k1, so in other words, what we're doing is we're first starting with t equals 0, and we find that for t equals 0, k1 plus k2 plus 1 equals 9. And then for the situation where t equals 1, we get that 5k1, that comes from here, minus 2k2, comes from here because t equals 1, plus 1 equals minus 1. When we solve these two, we get k1 equals 2, k2 equals 6. So the general solution in this case is yt equals 2 times 5 to the t plus 6 times minus 2 to the t plus 1. Now we can go a little bit further and look at the nth order equation. So a third order difference equation has a cubic auxiliary equation whose three roots may be distinct, multiple, or complex conjugate, so imaginary numbers, in various combinations. The same is true of higher order equations. So the homogeneous nth order solution, k equals 0 in this case, is given by yt equals k1 x1 to the t plus k2 x2 to the t, and so on, times adding until we get kn to the xn to the power t. Remember, the x1, x2, xn are found from the characteristic equation by solving it for x, and the values of k1 through kn are found from initial conditions. So we need an initial condition for time 0 equals c0, for time 1 c1, and so on for the time n minus 1 equals cn minus 1. If two or more xi are equal but real, some terms are multiplied by t or some power of t, as we showed in the case of the third order solution. If some xi are complex conjugate roots, they contribute cosine terms multiplied by RT. So it's these terms here that may not necessarily have this kind of a form, and we may need to add a t in here, or t squared or something like that, or even cosine terms. But the case of the second order non-homogeneous equation adequately illustrated all of the possibilities that we might encounter. So that's why we don't go any further than the second and third order cases. Thank you for watching this video. There are many more videos in this 2 to 3 course series. A list of videos, the order in which they should be taken, and links to them are found under Mathematical Economics at the website indicated below.